This is a course on advanced theory of elasticity. So this certainly requires that you know the basic elasticity. So for example, if you have a very good knowledge of strength of materials from UG, strength of materials or mechanics of materials or solid mechanics, whatever you call it in your undergraduate college. So you should know it well. Okay, so this is the UG course. If you have any problem, please ask me. I am not able to see the chat window now. So please ask me if you feel any problem. Okay, then what are the reference books? So you don't have to buy any book. There are several online references available. Number one is this online link solidmechanics.org. Can you open this site, solidmechanics.org? Just try to open it now.
Yes, sir. By Professor Badal.
Yes. Similarly, there is another nice resource, which is lecture notes on mechanics of solids. Just write it on Google. Write it and try to find this page. Can you find it? If any one of you cannot find, please let me know. Are you able to find it?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
very good. So it has got two volumes, volume 1 and volume 2. Volume 2 has got mathematical preliminaries, which is required in any advanced solid mechanics course or continuum mechanics course. And there are several things here, but we will touch chapter 1, 2, 3, 5, and if possible 6 also, but we are not sure right now. Okay, and likewise it has got volume 2. So we will see how much we can cover in this class. Okay, but what we are going to learn is advanced theory of elasticity. For example, in your UG course, what you learned was just linear elasticity. Which holds only when displacement is very small. Okay, but what if the displacement is large? What if the body Just suppose that I have this body and it becomes like this. So there is very large deformation in the body. So linear elasticity fails when there is large deformation. Okay? And why does it fail? There are two reasons mainly. So in linear elasticity, we assume that strain is linear in displacement. And the other assumption is that stress is linear in strain. And these two together means that the equations of equilibrium are linear in displacement. If you have any problem, please ask me. If you can't see what I'm writing, if you want me to write more, bigger, just let me know. And that's why we call it linear elasticity. But whenever we have large deformation, then both these assumptions fail. Neither is the strain linear in displacement, nor is stress linear in strain. Okay, and that's why we call it non-linear elasticity. So, the first thing, of course, is linear elasticity. Whenever you get introduced to deformation, the basic course will only talk about linear deformation or linear elasticity. And once you have mastered linear elasticity, I mean, not really mastered, but let us say you have some idea, then you can learn about large deformation elasticity or non-linear elasticity. And this course is about non-linear elasticity. Okay? So, before really starting the actual material of this course, we have to get acquainted with the language of the course. So, what mathematics we are going to use while trying to understand the material of the course. So, whenever you do any advanced courses, no, that's the first topic that we learn. The mathematical, we can call it mathematical preliminaries to get you acquainted with the language of the course. And some of you may have seen it already. So the first thing is we are going to learn about what's called summation convention. So the students who are doing continuum mechanics right now, have you done it already?
Yes, sir.
Pulkit, for
Yes, sir.
example, have you done it?
That engineering maths and computation, it is going on.
It is
And
going on.
yes, sir. And in the continuum also, like some introduction is given about that. Means it is going on, sir.
Okay. All right. So let's also do it here. So suppose the simplest example that we can start with is the matrix equation. So you all must be aware of this equation, a11x1 plus a12x2 plus a13x3 is equal to b1. Then let's say a21x1 plus a22x2 plus a23x3 is equal to b2. And finally a31x1 plus a32x2 plus a33x3 is equal to b3. Okay, so we know that this can also be written as a matrix equation. So you have a matrix A multiplied with the vector x, giving you the vector b, isn't it? And then its solution is x equal to A inverse b. Okay, and sometimes people also write it in a slightly different manner. So you see this itself. The first equation, for example, is summation over I equal to 1 to 3 a1i xi, that's equal to b1, isn't it? The second equation is summation over I equal to 1 to 3 a2i xi is equal to b2, right? And if you want to generalize this, I could say that it's summation over a ki, and there's summation over I into xi, and that's equal to bk. Are you with me?
Sir.
For
Yes,
example,
sir.
Niranjana, are you
Yes,
with
sir.
me?
Yes, sir.
Niranjana, who is okay. Saurabh, Devji,
Hello.
yeah. All right. So now summation you see, writing this summation symbol all the time is very cumbersome. And summation convention allows us to get away with this symbol and simply write this as AKI XI is equal to BK. But then we have to interpret it. So you can see that this subscript I is repeating, right? So whenever you have a repeating index, that means there is a summation over that subscript. Okay, so that's the rule here, that repeating indices are summed. And there are actually several rules of the summation convention. Okay? This repeating index, this is also called dummy index. Why is it called dummy index? Because this is just a variable of summation. You can replace I with any other symbol also. Let's say you can replace I with J. So this thing is equivalent to writing AKJ XJ is equal to BK. Okay, so you see I got replaced with J because it is just a variable of summation, isn't it? So therefore it's called a dummy index. It's dummy. Whereas the other index that is present here, this K, which is appearing only once, That's called free index. Okay, so dummy index is going to repeat twice, whereas free index appears only once. You might say that key is appearing twice, one on the left hand side and one on the right hand side, isn't it? But when you count, you just have to count on just one side, not on both the sides. Okay? And you cannot replace free index with anything else. For example, when you have this expression akj xj equal to bk, you can't say that this is equal to amj xj is equal to bk. So this is not the same thing. Of course, you can say that amj xj is equal to bm. This is perfectly fine because you change the free index both on the left hand side as well as on the right hand side, then it is fine. But if you change the free index only on one of the sides, then it is not correct. Okay. The other thing is, so let me, first of all, write down the entire rule of this summation convention. So as I told you, first is repeating indices, which are also dummy indices, are summed and an index may appear only once or twice. It cannot appear, it cannot appear more than twice. Okay, so you can't have an index appearing 3 times, for example. If it is appearing only once, so appearing only once, then that's the free index. And appearing twice, that's the dummy index. And the last thing is, all terms in an expression must have the same free index. What does this mean? For example, if you have an expression like amkxk plus bmyxy is equal to, let's say, vm. So you see m in each of the terms, m is appearing only once. So therefore it's the free index, okay? And it has to be the same m. It can't be that you say amkxk plus bny xy is equal to vm. So this is not fine, because in this term you are writing your free index as n, so that is not correct. Similarly, as I wrote above, it is not allowed to say like this. So a nk xk yk. So this is also not correct. Why? Because k is appearing thrice. Let me give you an example which will tell you that an index should not appear more than twice. Okay, so suppose that so all of you know about this dot product, isn't it? Suppose you have a vector A and I am dotting this with vector B. Then what is this? From your usual convention, this summation over I equal to 1 to 3 AIBI, isn't it? And this we are going to call it as AIBI, correct? Now let us say I want to have A dot B magnitude whole square. Okay? So this double bar is used to denote magnitude of a vector or tensor. So double bar is for magnitude of a vector or tensor. And if it's just one bar, that's for a scalar. So if you have something like this, so this is for magnitude of a scalar. Okay, now let us try to write down this A dot B magnitude square in summation convention. So how would we have done in the usual way? It would have been summation over I equal to 1 to 3 AIBI and then whole square, isn't it? Now somebody could also think that, okay, I can also write this as summation over I equal to 1 to 3 AIBI into another summation over I equal to 1 to 3 AIBI, correct? So if you are writing like this, there is no ambiguity. We know what does this mean. But let us say now I drop this summation symbol because I want to use summation convention. I drop this summation symbol and say that this is equal to AIBI into AIBI. Okay. So here you see I is appearing 4 times. Now, what is the problem with this expression? Suppose that somebody directly gives you this expression, and then you have to think of what does this mean. Then you might interpret it as there is a single summation over I equal to 1 to 3 AIBI AIBI, isn't it? So you see, this is not what you wanted, right? This is not what it is. So we should not write like this. So what is the way out? We could write this as I told you, an index does not have to appear more than twice. Then we could write this as I equal to 1 to 3 AIBI and another one summation j equal to 1 to 3 AJBJ. This is also perfectly fine, right? because I or j here are dummy indices. So you can use any symbol. And then you forget about the summation symbol and write it as ai, bi, aj, bj. And then it has got only one meaning. So I is repeating twice, that means there is a summation over I, and j is repeating twice, that means there is also a summation over j. So this is then double summation over I and j, ai, bi, aj, bj. And this is exactly what it is. Okay? So you can see that why we made this rule that no index should appear more than twice. Okay, we demonstrated it through the example where I was appearing 4 times. You can likewise think of an example where an index is appearing thrice, and you will see that this will not make sense. All right.
Excuse
So
me,
that's
sir.
the rule. Yes.
Sir, does free index will appear in each term? Means is it compulsory?
Please say again.
The free index,
Yes.
will it appear in each of the term of an expression?
Well, it depends on. So that's a very good question. So right now, when we wrote this thing over here, you can see that this free index is appearing in each of the terms. Sometimes you can have a expression having more than one free index.
Okay.
Then you have the flexibility. But for now, let us just assume that there is only one free index, and then it's going to then it has to appear in each of the terms, okay? And it has to be the same free index.
Okay, sir. Thank you.
Yes. Any more question? No more question? Okay, the other thing, so this is all about summation convention, but we will do lots of examples with summation convention, so you get used to it. And this is very important because you will see first of all, what is the advantage of having summation convention is that it compacts your notation. It compacts your expression. You see your first case here itself. This big thing, you are able to write this as aij xj equal to bj. So it has compacted your notation, isn't it? So that's the advantage of summation convention. And that's why we are learning it. You could also think of using this notation, right? This is also a compact notation. But often it is not so easy to think of this notation. Here you are able to think of this compact notation through matrix and vectors. But it is not always possible to think like this. You will see such examples later on. Okay? So don't worry, you'll get used to it. And why, what's the use of it? All right? Okay. The next thing is what's called Kronecker delta. So I guess you have learned about this also. Kronecker delta function. So it is denoted by the symbol delta. And it has got two indices I and j. And its definition is that this is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. Okay, so this is simply the definition of Kronecker delta. Let me try to use this Kronecker delta in a summation convention. So suppose I have this expression aij delta ij. So what does this mean? So here you have I also repeating and J also repeating, correct? So it's basically double summation. Now think of just expanding J summation. So this becomes summation over I, AI1 delta I1 plus AI2 delta I2 plus AI3 delta I3, isn't it? Now you see this delta I1, delta I2 and delta I3. Only one of them is going to be non-zero because of this definition. If I is equal to 1, then delta 1, 1 will be 1 and delta 1, 2, delta 1, 3 are all 0. Isn't it? So basically, this could then be written as summation over I, AII. Can you see why? Because from these three terms, I had to take only one of the terms. Rest two will certainly be 0. And which one I have to take? It has to be the one where this 1, 2, 3 is I. Because only that one will give you delta II being equal to 1. Can you see this? Anybody having difficulty here? So you're not saying anything. Does it mean you're not understanding? Yes?
Understanding, sir.
What about Saurav? Are you understanding?
Sir,
Are you able to understand this?
sir, I have one question.
Yes, sir.
Yes.
Sir, like here, Aij, delta Aj, like it will consist of 9 terms.
Yes.
So, means how did you how to convert from the right hand side what you have written AI1 delta I1 plus AI2 delta I2 plus AI3 delta I3 into AII? Like if we have a large number of terms, so
Right.
how we will directly go to AII?
Okay, that's a good question. So that's what I wanted to see whether you are able to follow it. Maybe, let us try to write all the 9 terms here. So what will they be? It's going to be A11 delta 11 plus A12 delta 12 plus A13 delta 13 plus A21 delta 21 plus A22 delta 22 plus A23 delta 23 plus A31 delta 31 plus A32 delta 32 plus A33 delta 33, isn't it? Now, which of these are going to survive? It's just these ones. Rest all are 0, correct? Because of this
Yes, sir.
definition of Kronecker delta. So this
Yes,
has
sir.
become A11 plus A22 plus A33, isn't it?
Yes, sir.
And can I not write this as AII,
Yes, sir.
right? And that's what you see, this is what I wrote here.
So, sir, after you expanded it in terms of J, then
Yes,
we can combine the dummy variable which is left here to go to the final step. Like I is
yes.
left.
So basically, if I have to sum what I just saw here is that, so whenever you have an expression Aij delta Ij, then what you have to think is, look for the repeating index from delta. Here you have I and j both repeating. Just take one of the index, let us say j. So what Kronecker delta does is it annihilates that repeating index. It annihilates the summation of the repeating index. It gets rid of the summation and replaces that repeating index with the other index of Kronecker delta. This will become more clear if you have something like this: A I delta ij. So here you see I is repeating, isn't it? And there is summation over I. So what Kronecker delta function does is it removes that summation over I and replaces I with the other index of Kronecker delta, which is j here. So this becomes simply aj. So what it has done is removes summation over I and replaces I with j, which is the other index of Kronecker delta.
Okay.
So if you apply this logic here, so think of, let us say I want to think that I is repeating here, okay? I is repeating. So
Yes,
when you
sir.
apply this logic, it says you have to remove the summation over I. So essentially you replace I with j, okay? And replace I with j. So in
They both are
aij, you replace I with j. This is ajj. The other way was, you could also see that j is repeating here. So here you have both the option. I is also repeating and j is repeating also. So you can go either way. So if you think through j, then we will say that remove summation over j and replace j with I, which is the other index of Kronecker delta. And then it becomes aii. But ajj is same as aii because, as I told you, it's a dummy index and it's the same thing then. I hope you are able to follow this.
Yes, sir.
Similarly, suppose you have CIJKL into, let's say, AJK into Kronecker delta LM. And let's say there's another one, which is AMI. So first of all, is it a valid summation expression? So you have I, J, K, L, M, and all of them are appearing twice, isn't it? So it's a valid summation. None of the index is appearing more than twice. And there is no index appearing only once. That is also perfectly fine. In an expression, you don't need to have a free index. Okay? Now, I have to think, what is this going to become? So there are two ways to proceed. In this Kronecker delta, both L and M are repeating. So you can proceed by choosing either L or M. Suppose I see that L is repeating here, right? L is repeating here. So there is a summation over L. So what I will do is, I remove the summation over L and replace L with M. So replace L with M, which automatically removes the summation over L. And how did I know that I had to replace L with M? Because M is the other index in Kronecker delta here. So this becomes CIJKM AJK AMI. Okay. The other way was, so that is this way. The other way is that I see that here M is repeating, isn't it? M is repeating. So in this approach, the summation over M gets annihilated. And wherever you have M, it has to be replaced with what? The other index of Kronecker delta, which is L here. So this becomesCijkl Ajk into ALI. Okay. Now, so we did it in two ways, but are these two the same? Are they same? What do you think? Are they same? So what is the difference? The difference is in just this index L. Here you have summation over L, and here you have summation over M. But as I told you, repeating indices are dummy indices. You can replace that symbol with any other symbol. So L here you can replace with M, or M here you can replace with L. And both of them then become the same, isn't it?
Yes, sir.
Okay, so that's the advantage of having Kronecker delta function and how it operates. Basically, you got to know this. So once we have this Kronecker delta, then there's another one which is called alternator or permutation symbol. I especially want to check with the four students, Niranjana, Saurabh, Devjit, and Nomendra. I hope you guys are following it.
Uh, Sir, so the main function of Kronecker delta is to make our system of equations more compact. For example, Aij delta Ij, we can write it as Aii.
Yes.
Okay, sir.
So I mean, it's just a property of Kronecker delta that it gets rid of one of the summations, right? Because of the property of Kronecker delta, one of the summations will be gone, and the expression will therefore become a bit more compact.
Sir,
Yes.
sir, that Kronecker delta means, is it used because we are removing the summation sign? Means in order to make what terms we require?
Are you saying why do we need Kronecker delta?
Yeah, means if we don't use Kronecker delta, then we will get 9 terms. But like
Yes.
if we use Kronecker delta, we will get 3 terms.
3 terms. Yes. So it's not like why do we need Kronecker delta? Why do we use? It's like it's about if there is Kronecker delta, then what should we do? You don't have to use Kronecker delta. Suppose it is there in your expression, then how to evaluate it?
Okay.
That's what we are doing here.
Okay.
You will see that you will automatically have expression having Kronecker delta, and then you will have to deal with it. So this is how you deal with it. For example, do you guys know about orthogonal matrices? Orthogonal matrix, do you know? So you have a matrix Q. It is orthogonal if Q into Q transpose
Equals to 1.
is equal to
I
identity matrix. right? I hope you guys know this. And suppose this identity matrix, I want to write the components of this identity matrix. So this big I, little ij, ij component of this identity matrix, what is this? So this is exactly Kronecker delta ij, isn't it?
Yes, sir.
It's 1 on the diagonal and 0 on the off diagonal. So whenever you have an expression getting multiplied with an identity matrix, then you can see that Kronecker delta will automatically appear. Similarly, this thing here, when you evaluate this matrix multiplication, let us, for example, think of a matrix multiplication. Suppose you have A equal to B into C. Okay? Then what will be Aij? What is the ith row and jth column? So ith row and jth column is obtained by multiplying the ith row of B, which is bi1, bi2, bi3, with the jth column of C, C1j, C2j, C3j. So that's the ith column, sorry, ith row, and this is the jth column. Okay, that's how we get ij component of the multiplication of matrix, isn't it? I hope you guys know this. If you're multiplying two matrices, then the resulting matrix A, the ij component is you take the ith row of B and multiply with the jth column of C. Now you see, when you do this, what is this giving you? This is B I1 C1j plus B I2 C2j plus B I3 C3j, correct? Which is same as B I K C K J, isn't it? In summation convention. So Aij is basically Bik Ckj. Are you with me?
Yes, sir.
Yes, sir.
So suppose that I have this thing over here, QQ transpose equal to identity, Q into Q transpose equal to identity. Then what does this mean? What will be Ij? So I is the resulting matrix. So I is like your A here. So this is your A, sorry, this is your B, this is your C, and that's your A. And apply the above formula. So it says Iij is equal to Bik into Ckj, right? Now B is same as Q, so this becomes Qik. But C is equal to Q transpose. So what will be Ckj? So Ckj will be equal to Qjk. It's not Qkj, it is Qjk because C is equal to Q transpose here, isn't it? So this basically gives us that Kronecker delta Ij is equal to Qik Qjk. So you see, you have an expression in which you get a Kronecker delta. So this was a very simple example. You will likewise come across more complicated example or expression where you will automatically have Kronecker delta. And then you will need to know how to work with them. Okay? So having done this, let's now proceed to this alternator symbol. So we have this alternator or permutation symbol. Okay, so this is denoted by epsilon, and it has got three index, I, J, K, and they are all free indices. See, because all of them are appearing only one, so they are free indices. Okay, and what is the definition? The definition is this is equal to 0 if any two indices are same. This is equal to 1 if all three are different and in cyclic order. I will tell you what does this mean by cyclic order. And it is equal to -1 if all three are different but not in cyclic order. Okay, so this means epsilon 1 1 1. What is this going to become then as per this definition? So you see it has all the three indices repeated. So this is 0. What about epsilon 1 2?
1 to 0.
This is also equal to 0. Very good. What about epsilon 1 2 3?
1.
So this is equal to 1. And why do we say 1? Because it's a cyclic order. And how do we define the cyclic order? So it's as follows. You take 1, 2, and 3, and then it goes into cycle. So it can be either 1, 3, or 2, 3, 1, or 3, 1, 2. They are all in the cyclic order. Okay, somebody has his mic on. Please mute your mic. Okay. So these are all cyclic combinations, and so all three of them will give you 1. Okay, again somebody has his mic on.
Yes, sir. I'm actually asking question.
Okay, but what about epsilon 132? What is this equal to? So you see, coming here, when you go from 1 to 3 to 2, you are not going in the same direction, right? You go anti-clockwise. So the cyclic was if you were going like this, clockwise, and you find the indices. So 1, 3, 2, the sequence is such that you are not going in the same direction. So therefore we say it becomes -1 because the direction has reversed. Likewise for epsilon 3, 2, 1. So 3, 2, 1 is also anti-clockwise, right? So therefore this is also equal to -1. So this is for clockwise clockwise, what should we say? Clockwise movement, and rest is anti-clockwise movement. Okay. Now again, why do we need this epsilon symbol? What is the use of this permutation symbol? So, you guys know about the formula for determinant, isn't it? So determinant of a matrix, let us say determinant of A. So you have determinant of this matrix A11, A12, A13, A21, 22, 23, A31, 32, 33. Okay. Now what is the determinant? So this is A11 into A22, A33 minus A32, A23 minus A12 into A21, A33 minus A23, A31 plus A13 into A21, A32 minus A31, A22, isn't it? So I guess you guys know. So I have expanded it through the first row of A. Now this is a big operation or a big expression. This entire thing is a big expression. Can we make it compact by using summation convention? Then yes, you can do it, but then you have to use that permutation symbol. So this thing becomes epsilon ijk into a1i, a2j into a3k. So when you expand this expression, you will see that it becomes the same thing as this. So you can see the advantage of this permutation symbol, isn't it? It is used to denote the determinant.
Sir, how did you convert it?
Or how do I convert? So you really have to expand and see.
Okay.
Yeah. This is also used in cross product. You know, suppose you have cross product of two vectors A cross B. Then, I mean, you can find out now what are the components. So what does it turn out to be? This is, so I will write A as A1, A2, A3, cross product B1, B2, B3. So this is going to become, the first one will be A2, B3 minus A3, B2, I plus, for the J, it's going to be, correct me if I do some mistake, A3, B1 minus A1, B3, J, and the last one would be A1, B3 minus A3, B1, K, isn't it? So this is again a big expression. Is there a way to use summation convention? Then yes, it is there. You again have to use this permutation symbol and it becomes epsilon ijk aj bk ei. Well, let me make it e1, e2, e3. Then that way it will be easier. And maybe I can show this thing here for
So
I equal to 1.
so the
Yes, this
alternator
is,
symbol will always have three maximum indices. It cannot have more than three.
which way again?
So the alternator symbol, does it always have a maximum of three indices attached to it? Can it have more than three?
Yes. No, it always has three indices. Yeah. Okay, and you can prove it also. So let us try to verify, for example, the E1 component. Can we verify the E1 component? So to verify the E1 component, what should I do? I have to take I equal to 1, isn't it? If you take I equal to 1, what do you get? You have epsilon 1 jk Aj, Bk, E1. So you have summation over J as well as over K. And you know that if J becomes equal to K, then epsilon becomes 0. So J and K have to be different. So the only possibility is take J equal to 2 and K equal to 3, and J equal to 3 and K equal to 2. So you have 1, 2, 3 and 1, 3, 2. This gives you plus 1 and this gives you minus 1. So this becomes A2B3 minus A3B1 into E1, right? Sorry, A3B2. And you can see that this is indeed what it is here. So you see, this is the advantage of permutation symbol. Okay, any question on this permutation symbol? No question? Okay. You know, there is also a way, there is also a identity called epsilon delta identity. Epsilon delta identity, which is the following. So this says that epsilon ijk into epsilon pqk, this is equal to delta ip into delta jq minus delta iq into delta jp. Okay, so the first one is I here. So this is an identity which can be proved. And when can this be used? You know, suppose in an expression you have two epsilon symbol. Somehow you get two epsilon symbol. For example, if you have two cross products, then you will get two epsilon symbol, right? For each of the cross product, you will have one epsilon operator and two cross product giving you two epsilon symbol. And then you can use this relationship to convert your epsilons into Kronecker delta. And after you have gotten Kronecker delta, then you can use the Kronecker delta identity to compact the expression. Isn't it? Okay. And finally, you know, I could also make at many places you will see it's written in a different way. So for that, you have to understand that epsilon ijk is equal to epsilon ikj, but with a minus sign. If you flip the index, you have to get a minus sign. And if you again flip, let's say if you flip these two, then you get one more minus and then it becomes epsilon kij. And likewise, epsilon pqk is same as epsilon kpq. Okay? And seeing that, you could also write the above identity as epsilon kij into epsilon kpq being equal to Kronecker delta ip into Kronecker delta jq minus Kronecker delta iq into Kronecker delta jp. Okay? And you can see that it has got how many free indices? Can you see how many free indices are there?
4
So
free.
only K is repeating, rest all are free. So it has got 4 free indices: I, J, P, Q. So this is an example where you can have more than one free index. Okay. Likewise, on the right hand side also, you have those same 4 free index appearing. In each of the terms here, you have the same 4 free indices appearing. And the K here is a dummy index. You can replace K with any other, for example, M, N, O, but you can't make K as P, for example, because P is a free index here. So you can replace K with any symbol other than the free index that is present here. Okay? So I will, I will again start from here in the next class tomorrow. All right? If you have any question, you can, of course, ask me.
Hello, am I
Yes.
audible?
Yeah, yeah.
Sir, is it necessary that we should have same free indices in each term of a given equation? Like here we have four free indices. So,
Yes.
so is it
Yeah,
necessary that
I mean, usually it is necessary because otherwise it does not really make sense. Otherwise,
otherwise?
it does not make sense otherwise.
Okay,
Yeah.
okay, sir.
I mean, you see, the free index, what does it mean? That the free index means this equation is going to hold for every possibility of that free index. So IJPQ is present. So you can take IJPQ to be anything, any four number you take for IJPQ. Let us say you take I equal to 1, J equal to 2, P equal to 3, and Q equal to 1. Then this identity tells me that epsilon K 1 1 epsilon K 2 1 is equal to delta 1 2 delta 1 1 minus delta 1 1 into delta 1 2, and which of course is, by the way, 0, right? So this is going to hold for all the combinations of the free indices.
Sir, there are two things. So
Yes,
from chronicle delta, so one thing is what I understood, it is basically chronicle delta is what it is, and whenever we will be multiplying it with anything, it will basically replace the repeating index with its own index.
that is
So
true. With its other index.
yes, sir. And
Yes,
sir, other thing is like when we talk about matrices, so for example, if I multiply identity matrix with the matrix A, so like
yes,
matrix A into identity matrix will be equals to matrix A only. So sir,
correct.
it has any relevance with chronicle delta?
Yes, so that you can also show. So let me try to prove that through Chronicle delta. So suppose I have, let us say A into I is equal to C. Okay. So C is the resulting matrix which is equal to A into I. Okay. Then through the property of matrix multiplication, we know that Cij is equal to Aik into Ikj, right? The matrix multiplication just means that the inner indices have to repeat. The inner indices repeat. And now you replace Ikj with chronicle delta Kj because that's the property of identity matrix, no? So this becomes Aik into chronicle delta Kj. And as you just said, very nicely you said it, that its replaces the repeating index k